Hey there, and welcome. Today, we're diving deep into a real-life scientific detective story. We're heading right into the heart of matter itself to uncover how we, step by step, figured out the structure of the atom.
You know, everything you see, everything you touch, it's all made of atoms. But for most of human history, what they actually looked like was a total mystery. So the big question we're going to unravel today is this. What does an atom really look like? Let's get into it.
All right, here's our roadmap. We're going to follow the clues left by some of the greatest minds in science. We'll start with Thomson's first guess, then see how Rutherford's wild experiment blew it all up, leading to his solar system model, and finally, we'll see how Niels Bohr added a mind-bending quantum twist. It's a story where each step builds on the last. Okay, let's jump back in time to our first big clue. Our story really kicks off in the late 1800s with a physicist named J.J. Thomson. He gave us the very first scientific picture of what an atom might be.
So Thomson had just made this incredible discovery, the electron. And to make sense of it, he came up with what we now call the plum pudding model. Just picture a solid ball of positive stuff, like a cloud, and scattered all through it are these tiny negative electrons, kind of like raisins in a cake. The big ideas here were that the atom was a solid sphere, and all those positive and negative charges canceled each other out. Simple enough, right?
And for a while, that plum pudding model was the best idea anyone had. But then, one of Thomson's own students, a guy named Ernest Rutherford, set up an experiment that was about to become a total game changer. The experiment itself was brilliant. Seriously, so simple. Rutherford's team basically built a tiny particle gun. They fired a stream of these things called alpha particles, which are just small, dense, positively charged bullets, at a super thin sheet of gold foil, and they put a special screen around it to see where the particles ended up. Now stop and think about this. If the atom is really this soft plum pudding that Thomson described, what should happen? Well, Rutherford figured those little alpha particle bullets would just tear right through the gold foil, maybe getting knocked off course just a tiny bit. It should have been like firing a cannonball at a sheet of fog. But that is not what happened at all. The results were mind-blowing. I mean, truly shocking. Sure, most of the particles did fly straight through, just as he thought. But, and this is the part that changed everything, some were deflected at massive angles, and a very tiny number, we're talking like 1 in 8,000, came screaming almost straight back at the source. As Rutherford himself said, it was as incredible as if you fired a 15-inch cannon shell at a piece of tissue paper and it came back and hit you. So, what do you do with a result like that? It meant one thing for sure. Thomson's model was completely, utterly wrong. There was no way a soft pudding could ever send a high-speed particle flying backwards. It was time for a whole new picture of the atom. Rutherford pieced it together like a master detective. The fact that most particles went through, that meant the atom had to be mostly empty space. And for a positive alpha particle to get knocked backwards, well, it must have hit something incredibly small, incredibly dense, and also positively charged. He called this tiny center the nucleus. And the electrons? They had to be way out on the edges, orbiting this new nucleus from a distance. And just like that, the plum pudding model was out. In its place, Rutherford gave us this beautiful new image, a miniature solar system. You've got this tiny, heavy sun, the nucleus, smack in the middle, and these lightweight planets, the electrons, whizzing around it. This was a radical, revolutionary idea. But, you know, even this brilliant model had some major problems. It did a perfect job explaining the gold foil experiment, yeah, but it opened up two brand new, massive mysteries. First, basic physics said that a negative electron orbiting a positive nucleus should lose energy and just spiral into the center, making the atom collapse in a split second. And then there was this other really weird thing. See, when you zap a gas like hydrogen with energy, it glows. But it doesn't just glow with a smooth rainbow of colors. Nope, it emits light only at very specific individual lines of color. This is called its emission spectrum, and it's basically a unique barcode for every element. Rutherford's solar system model had absolutely zero explanation for why this happened. And that's when the next hero of our story, Niels Bohr, stepped onto the stage. He took a look at the holes on Rutherford's model and came up with a solution that was so radical, it basically invented a new kind of physics to make it work.
Bohr's entire idea hinged on this new concept he called the quantum. Now, a quantum isn't just a random bit of energy. It's a specific, fixed amount. The best way to think about it is like a staircase. You can stand on step 1, or you can stand on step 2, but you can't hover in the empty space between them. For electrons, Bohr said energy works exactly the same way.
So Bohr laid down a few new rules for the game. Rule number 1, electrons can only exist in fixed energy levels, or orbits, no in-between allowed. Rule 2, as long as an electron stays in its orbit, it doesn't radiate or lose energy. That right there solved the whole atom collapsing problem instantly. And then, here's the absolute genius part. An electron can jump up to a higher level, but only if it absorbs the exact right quantum of energy. And when it falls back down, it spits out that exact same quantum as a little flash of light.
And just like that, the mystery of the line spectrum was solved. Each one of those colored lines for hydrogen was just an electron falling from a specific high step to a specific low step. A big drop from, say, level 5 down to level 2 that releases a lot of energy, giving you a violet or blue line. A smaller drop that's less energy, giving you a red line. It was perfect. Bohr's math predicted the lines with incredible accuracy.
Bohr's model was, without a doubt, a huge leap forward. It brilliantly combined Rutherford's nucleus with these new quantum ideas. But, as it always goes with science, the story was far from over.
You see, Bohr's model was a rock star, but only for hydrogen, the simplest atom with one electron. As soon as you tried to use it for helium or anything bigger, it completely fell apart. It couldn't explain their much more complex light shows. And at its core, it still pictured the electron as a tiny little ball, when new discoveries were showing that electrons were much, much weirder, acting like waves and existing in fuzzy 3D clouds.
But you can't look at these as failures. Not at all. In science, when a model has flaws, those flaws become the most important clues. They're like a treasure map, pointing the way for the next generation of scientists to dig deeper and find a more complete truth, which is exactly what led to the modern quantum mechanical model we use today.
Which brings us to one last, really important question. If Thomson's model was wrong, and Rutherford's was incomplete, and even Bohr's had big problems, why do we even bother learning them? We learn them because they show us what science actually is. It's not a dusty book of facts. It's a living, breathing story of curiosity, evidence, and constant improvement, a journey that is still going on.